Let's dive right into this explainer and finally demystify the 80 years of research and, quite frankly, elegant math that powers modern AI. You know the feeling. You type a prompt into an LLM, like ChatGPT or Claude, hit enter, and the response you get back feels completely magical. Well, today, we're going to look under the hood to prove it's not magic at all. It is literally just highly sophisticated pattern matching.
To give you a clear map of our journey today, we are going to replace that mysterious AI black box piece by piece. We're going to follow a single prompt from your keystroke to the final generated response across 6 key steps: the illusion of intelligence, breaking down the language, the math of meaning, the transformer engine, predicting the next word, and finally, more than just autocomplete.
All right, let's kick things off with step 1, the illusion of intelligence, from chatbots to neural networks. Because to really grasp modern AI, we first have to look back at how we originally tried to fake it.
It's kind of crazy to think our quest actually started over 70 years ago. Back in 1950, Claude Shannon was playing a language guessing game with his wife just to prove that written language has a deep underlying statistical structure. That exact same year, Alan Turing proposed his famous test for machine intelligence. But it wasn't until 1966 that Joseph Weizenbaum built ELIZA, which was basically a chatbot mimicking a therapist. Now, ELIZA had absolutely zero actual understanding. It just used basic programming to mirror your own words back to you. But it was so convincing that Weizenbaum's own secretary asked him to leave the room so she could talk to the program privately. It tricked people using incredibly simple rules. The really crucial takeaway here is that the jump from early bots like ELIZA to the massive language models of today isn't just a matter of someone writing a slightly better chatbot. We're talking about a complete shift in architecture. We completely abandoned manual rule-based systems, where a human had to literally type out thousands of if statements, and moved to neural networks. In a neural network, interconnected nodes process information using weights and biases. And thanks to a massive breakthrough paper in 1986, we learned how to tune these networks using a brilliant mathematical process called backpropagation. Basically, the system makes a guess, measures how wrong it is, and then adjusts its own weights billions of times until it gets it exactly right.
That brings us to part 2, breaking down the language, and the secret of tokens. See, before a neural network can even begin to process your prompt, it has to chop it into pieces it can actually digest.
Models simply do not see words the way you and I do. They see tokens. A token could be a whole word, it could be a single space, an emoji, or maybe just a fragment of a word. And to decide exactly where to split the text, models use an algorithm called byte pair encoding, or BPE. What's super surprising is that BPE was actually invented way back in 1994 entirely as a data compression trick, long before anyone thought to use it for language models. So how does BPE actually work? Instead of a programmer painstakingly writing down every single word in the English dictionary, BPE looks at a massive dataset and iteratively merges the most common character pairs. For example, it merges T and H to make TH, and then merges that with E to make the token the. Rare words get broken down into smaller, bite-sized chunks, while really common words stay whole. It's a completely automated puzzle. It handles English, Japanese, and even Python code automatically, without needing a single language-specific rule.
Moving right along to step 3, the math of meaning. Because right now, well, our tokens are just arbitrary numerical IDs.
We need a way to give those IDs actual meaning, and we do this using a brilliant concept called embeddings. There's a great quote from British linguist J.R. Firth in 1957, "You shall know a word by the company it keeps." That idea right there is the absolute foundation of modern distributional semantics. The thesis is beautifully simple. Words that appear near each other in training data get mapped closer together in a mathematical space.
Which leads to one of my absolute favorite concepts, word math. When researchers at Google trained an embedding model called Word2Vec, they found that it organized words logically without any human intervention at all. If you take the mathematical vector for kitten, subtract the vector for cat, and add the vector for dog, the closest resulting vector in the entire system is puppy. Seriously, nobody taught the model what a dog is, or what gender or royalty are. Those concepts just naturally emerged purely from the statistics of which words appeared next to each other words in the raw data.
And to capture all that incredible nuance across human language, you need a massive canvas. A basic 3D vector just uses an X, Y, and Z coordinate, right? But modern embeddings are unimaginably dense. To put it into perspective, the largest GPT-3 model maps words across a mind-bending 12,288 mathematical dimensions. Every single token you type gets assigned a coordinate in this massive space, just to capture its exact semantic flavor.
Okay, on to part 4, the transformer engine. Attention is all you need. We have our embedded tokens, sure, but how does the machine process them all together without grinding to a halt?
See, older models process text sequentially. They read one word at a time, which is painfully slow and meant they often forgot the beginning of long sentences by the time they reached the end. Then in 2017, a team of Google researchers dropped a completely free 15-page PDF paper called Attention is All You Need. They introduced the transformer. This architecture dropped sequential processing entirely, allowing the model to look at every single word in the sentence all at once. That single 15-page document is quite literally the blueprint powering today's entire trillion-dollar AI industry.
Inside the transformer, the real magic happens in a step called self-attention, which is powered by billions of matrix multiplications. Think of it like a lightning-fast matchmaking service for words. For every token, the model creates a query, a key, and a value. The query is what a token is looking for, the key is what a token offers, and the value is the context passed along when they match. This allows a word like bank to mathematically check its surroundings and instantly know if it's sitting next to river, meaning a muddy riverbank, or next to deposit, meaning a financial institution.
Which brings us to part 5, predicting the next word, one blind step at a time. After gathering all that rich context through the transformer layers, the model has to actually give you an answer. But here's the thing, the transformer doesn't just confidently spit out one single word. Its raw output is essentially a massive list of scores for every single token in its entire vocabulary. We use an algorithm called softmax to turn those scores into clear probabilities. Then, a setting called temperature decides how we sample the winner. A temperature of 0 means the model will strictly, rigidly pick the most mathematically likely word every single time. Dial up that temperature and it gets more creative, occasionally picking slightly less likely words to make the text feel a lot more natural and human. And this creates what we call an auto-regressive loop, because once it picks that single winning token, it appends it to your original prompt and runs the whole massive calculation all over again just to get the second token. I cannot stress this enough. The model has absolutely no grand plan for how a sentence ends when it starts typing. None. It is quite literally just blindly predicting one step at a time based purely on statistical probability. Finally, we reach part 6, more than just autocomplete, building the chatbot experience. Because up to this point, what we've actually built is just a wildly sophisticated autocomplete engine.
Turning that giant autocomplete into the super helpful assistant you use every day requires a few final, crucial adjustments. First, it undergoes pre-training on petabytes of raw internet text. Then, it's fine-tuned on highly refined question and answer pairs, so it actually learns to reply in a conversational tone. But it doesn't stop there. Next comes RLHF, reinforcement learning from human feedback. This is where companies actually pay real humans to rank the AI's responses, training it to prioritize helpful and safe answers. Finally, they teach the model tool calling. The model learns to output structured JSON code that can tell an external program to go browse the web, check the local weather, or execute a Python script. And then it appends those results seamlessly back into your conversation.
You know, while the math we've covered today, embeddings, matrix multiplication, softmax, is fundamentally straightforward, it's the sheer, staggering scale of modern models that makes them so capable. We're talking about models with 120 billion tuned parameters, sometimes way more. It's at this massive, unprecedented scale that all this simple math combines to create the highly convincing emergent behavior we interact with on our screens.
Ultimately, replacing this black box piece by piece leaves us with a pretty profound realization. These machines, they don't think like we do. They have no internal reasoning, no biological brain. They are entirely constructed from the statistical structure of human language itself, which leaves us with a really fascinating question to ponder. By completely mastering next token prediction, have we actually recreated human intelligence? Or have we birthed an entirely new, completely alien intelligence? Definitely something to think about the next time you hit enter.